All right, section 2.1 is dealing with measures of position. Mean, median, and mode are measures of center that we discussed before. They do measure position, but they only measure middle position. So how do we describe relative to position of other data points? Well, one technique is percentiles, and another one that we've talked about before is quartiles. So the definition of a percentile, the pth percentile of a distribution is the value with p% of the observations less than it. So maybe you get your PSAT results back and they tell you you're at the 34th percentile. It doesn't mean you got 34% of the questions right. It means you scored better than 34% of your peers. So it's a measure of position. So the median is actually the second quartile, which is the 50th percentile. So we use this kind of notation here for percentiles. Q1 is the 25th percentile because 25% of the values are less than it. And Q3. Major League wins in baseball. Here's a stem plot that shows the number of wins for each of 30 Major League Baseball teams in 2009. Okay. So they want us to calculate and interpret the percentile scores for the Colorado Rockies, who had 92 wins, and two others. I don't know if I'll do all three, but let's just do maybe one or two. So Colorado Rockies had 92 wins. That's that data point. So I'm supposed to count the values that were less than it, but there's a lot of them. So I'm just going to count the ones that were bigger than it. 1, 2, 3, 4, 5. And then 6 is that data point. 30 minus 6 would give us 24. So they had 24. They scored better than 24 out of the 30 teams. Type that in your calculator. I think that's 80%. So that is the 80th percentile. And then to interpret it, we simply state that they scored, or they had more wins than 80% of the teams. The Colorado Rockies won more games than 80% of Major League Baseball teams. Major League Baseball teams in 2009. Now, maybe just kind of to illustrate one more, the Yankees had 103 wins. That was actually the top win for that season, number of wins for that season. But they wouldn't be at the 100th percentile because there are 29 teams that were less than them. So they would be 29 out of 30, which I think is, I calculated it before, 96. That would be the 97th percentile. So you can't always, the highest score isn't going to be the 100th percentile all the time. Oftentimes it's like the 99th percentile. However, the lowest number of win teams, the team that scored the least number of wins, oh my gosh, I can't even talk. You know what I'm talking about. Those guys would be at the 0th percentile. Are percentiles and percentages the same? No, of course they're not. They're different. How are they different? Well, percentages measure parts of the whole. For example, if you take a test and you get an 80%, that means you got 80% right and 20% wrong. Whereas percentiles measures something completely different. It measures the position in a data set. Okay. When reporting grades to parents or students, what's the advantage of reporting percentiles? Makes it easier to compare yourself with your peers. With other students, I guess I should say. So if I see Bernoulli is at the 45th percentile, I know that he's performing better than 45% of his peers, and 55% are performing better than him. What's the advantage of reporting a percent? Like you got a 83 average. Well, first of all, that 83 average, that determines your grade. So you could argue that that is the most important thing, kind of. But it kind of measures the level of mastery. You could argue that who cares what everybody else does, right? I just want to know, is my kid understanding the material? Well, then that would be this. One common graph that utilizes this idea of percentage is called a cumulative relative frequency graph, also called an ogive. This is a graph of the age of the president at the time of their inauguration. So as you can see, the x-axis ranges from 40 to 70, spans from 40 to 70, meaning the youngest president was probably right around somewhere between 40 and 45, and the oldest was right around, I think Trump's actually 71. He's not in this data set though, because I made this data set before he was president. But what it does is it accumulates the data points as you span across this range. So you're always going to start at 0, and you're always going to eventually get up to 100% of your data points. Why does the graph increase at a slow rate at the start? You can see these have a low slope. That means basically there's not very many presidents from ages 40 to 50. Not many presidents aged 40 to 50. Why does the graph increase so fast here? Why is the slope so much steeper? Well, from here, I mean, from 50 to 60, you're going from 80% to like 20% to 80%. So that means 60% of the data points are between 50 and 60. Many presidents were aged 50 to 60. So the steepness of the line kind of tells you how fast you're accumulating those data points as you sweep across the x's. What was the oldest age of the president? I think I mentioned that before. We really don't know if it's the one I give you tomorrow is going to have a lot better resolution. This one kind of just hops in 5-year intervals. So I'm going to say between 65 and 70. I don't really know exactly. Years old. Approximate the 25th percentile. All right, so this is where these graphs kind of shine. That's the 30th percentile. So if we just kind of project across at 25 and then project down, looks like it would be, so the 25th percentile, also known as the first quartile, looks like it's right around 51 years old. So when you look at a box plot, you can't, or a box plot, I guess you can, a dot plot, you really can't see percentages, but here you can pick out any percentile you want at a glance. Estimate the IQR. IQR is Q3 minus Q1. So I already got Q1, let's try to find Q3. Q3 is, there's 70, so 75, go straight across, drop it down, let's say 60, 59 maybe, just an approximation. 59 minus 51 equals 8 years old. Obama was inaugurated at 47. Was he unusually young? Well, I don't know. Let's see his percentile score. 46, 47, 48, 49. So it's about there. And if you project straight across, looks like about 10% to me. So I don't know. Is being right at the 10th percentile unusually young? I kind of consider unusually young to be that 5% mark. So I'm going to say no. No. 10% of the presidents were younger. So this is not unusually young. Now, if you wanted to say answer yes to this, you could. You would just say, yeah, he was unusually young. There's only 10% that were younger than him, so that's pretty young. Use the graph to create a relative frequency histogram. Ooh, geez, that sounds like some work. This is a cumulative graph. Relative frequency histogram is going to look like, well, we'd start at 40 and then go 45, 50, 55, 60, 65, 70. These are our ages. And then we would have a vertical axis that would be relative frequency or percentages here. But I don't want it to accumulate. I don't want to keep getting up to 100%. I want to know what percent was in each of these bins. So I can actually calculate that from this picture. So I started at 0% and I went up to, what do you think, maybe 5%? So I accumulated 5% of the data points in this cell. So that's going to be I'm going to graph that 5% right here whenever I get to that. But let's find all of them. So then I go from 5% to what looks like about 20%. So 20 minus 5 is an extra 15%. And then to get up to this data point, looks like it's about 50 minus 20 is, so there's 30%. That's why it's steeper. And then this one looks like it's maybe about 80. 80 minus 50 is another 30%. And what does this one look like? Let's say 91% there. We don't want to round to everything. So 91 minus 80, that's an 11%. And that leaves 100% minus the 91 is the last 9%. All right, so those are my, not cumulative, but my actual relative frequencies. So to plot that, I guess we should scale this axis here. Let's go 5, 10, 15, 20, 25, 30. And from 40 to 50, we got 5%. 45 to 50, we got 15%. And then 30%. Then another 30%. And then an 11%. And lastly, a 9%. So now we have, instead of a title, histogram of president's age at inauguration. So it's a little bit of work, but you can do it. Okay. So that's it. Tomorrow we'll talk about z-scores. We'll talk about who's the greatest home run hitter of all time. Looks like fun. And then we'll talk about transforming data. Okay. Thank you.